Ladies and gentlemen, on behalf of the director of the Austrian Center for Digital Humanities, Karl-Heinz Mörth, who unfortunately could not join us today on account of a teaching obligation at the university, I would like to welcome you to another edition of our ACDH lecture series. We are starting the new season 2017 with a lecture by Professor Björn Ommer, who will talk about visual analytics, enabling images to speak for themselves. Our Austrian Center for Digital Humanities was founded with the declared goal of fostering new methods within the humanities and supports the endeavors of researchers working with digital tools. It was in pursuit of this goal that we established this special ACDH lecture format about 2 years ago. In this ongoing series of lectures, researchers, practitioners, and experts from various branches of the humanities reflect on the significance and impact that digital research is already having in their fields. We invite outstanding international scholars to share their insights about the future direction of DH, and we also hope to inspire the next generation of researchers, convincing them of the usefulness of DH. With these lectures, we are reaching out to all members of the humanities community, and at the same time, we are also aiming to react to the needs and the suggestions of particular groups within the DH community. By inviting Björn Ommer, we have done just that, fulfilling a long-held wish of art historians within the academy. To our great satisfaction, the registrations have shown that his lecture also attracted the interest of researchers from other fields, such as classical archaeology, medieval studies, Byzantine studies, and even high-energy physics, and it is our great pleasure that colleagues from the Danube University Krems at the Department of Image Science will also join us today. Thank you for your interest and participation. If you are interested in documentation, I can recommend our website, where we will provide Björn Ommer's slides. And I'm also pleased to inform you that we have established our own YouTube channel for the ACDH lectures, where you will soon be able to find a recording of this lecture. My colleague Richard Kurdiovsky will now continue with a short introduction and will also lead the discussion afterwards. Before handing over the podium, I would like to take the opportunity to thank all those who were involved in preparing this ACDA lecture, especially my team colleagues from the working group Networks and Outreach. Enjoy the lecture, and please feel free to join us for a glass of wine afterwards. Thank you.
Well, it is now my task to introduce Professor Björn Ommer from Heidelberg, where he is full professor for computer vision, as you've already seen just before. Actually, I'm personally very glad that you came to Vienna to give us an insight in the studies you are doing in your research. A topic that sounds a bit, for art historians, a bit challenging, so to say, concerning the question, well, if machines can do art historians' work, why should we continue as persons to do our research? But I'm sure you will teach us otherwise, as we've just discussed in the last hour. Björn Ommer studied computer science and physics in Bonn. He had his promotion at the ETH Zurich, doing pattern analysis and machine learning. He stayed in Berkeley for a time to do his research. And you probably know, and he might also mention the different research projects he's doing based on illustrated manuscripts and analyzing visual patterns there. Actually, you are much more competent to speak about this, so I'll hand over the podium. The stage is yours. Thank you very much.
All right. Thank you for the kind words. Thanks for having me here. It's been a real pleasure. We already had a really nice discussion in a small circle, and that exchange of ideas was really great. I'd now in this talk like to discuss how we can teach computers so that eventually they will enable large image data collections to really speak for themselves, so that they can actually reveal the intrinsic structures within these data sets. And I'd like to point out ways that we can actually turn these machines into valuable assets, which would actually help us in the humanities to actually open up new avenues for research. Now, to start, I'd like to point out that images have always been a defining element of cultural heritage for basically all of human history. So images have been pointing out like what we do and who we think we are. We have utilized them to actually show where we are, what we want to be, and eventually also how we feel and where we might want to be sometime in the future. Moreover, or exactly for that reason, the number of images has been and is continuing to increase exponentially, which you can easily see, not just analog photography, but also digital imagery these days. So we have lots of images out there, and with large-scale digitization projects in the field of arts and humanities, a lot of these image data is now easily available over the internet and large repositories. I mean, you can see a lot of examples here where you have millions or even hundreds of millions of images which are there. So the focus has really shifted. Years ago, the problem was accessing data. You need to go to a library, and the images that you were looking for might not be present there. You need to go somewhere else. But these days, the problem has shifted. We're actually in an age where, as John Naisbitt once said, we're really drowning in information. At the same time, we're starving for the knowledge that is within these collections of data. And that's kind of the problem that we actually want to now tackle. Now, is that really a problem? I mean, there has been a revolution in information technology. If you just go back a few decades, then you had storage, which filled full shelves, like this one here, that was like 20 gigabytes of storage space. And just the power button of that machine here has roughly the size of like an SD card, which holds more data than this whole storage space back in the 1980s. So a lot of things have changed. Storage is cheap, is easily available, so that's not a problem that we have anymore. But the and the storage has actually enabled these large data sets. So that's for sure. In large repositories, these days actually become possible because we can actually save them all on a digital hard drive, for instance. Then we have large networks which enable easy access to them, so that's also great. But the problem has shifted. These days, the problem is not so much like that this data is not available, but our problem has shifted from storing, from processing, from sharing the data, to actually finding the actual content that we want to retrieve. And that's the problem that we actually want to solve. One obvious or one first solution might be just mere textual annotations. And with almost all repositories that have been recorded over the years, people have spent like tedious amounts of work in not just annotating them, but maybe even coming up with full taxonomies for the data that they've been digitizing. So this has been a tedious manual process. You know probably lots of these projects here. But the problem is that this textual information that people have put into these repositories is lacking. It's lacking in several ways. First of all, the object categories that you might be interested in are, by definition, hierarchical in nature. And the person that has been annotating them might not have conceived the particular level of the hierarchy that you now, when you do research, are interested in. It might even be that you're looking for an artifact for which they basically did not have the necessary terminology. And then there's another problem, and that is that these taxonomies are lacking, or these textual annotations are lacking information on the location of objects in images. They can tell you that there is an object, but not where it is. But we all know that this plays an important role. If you look at this crown here, it plays a different role if it's here or if it's here on the ground in this particular location. So location is important also for the semantics that this image wants to communicate, and this information is just lacking. If you just have a label, there's a crown in that image. And last and most importantly, relations matter. Relations of objects within an image and relations between images. I strongly believe that one of the main points of the scientific endeavor has always been to bring entities into perspective, into relation to another, that are not there on the same page of a piece of paper. Putting things together which others might not have conceived of doing so, establishing relationships between objects that people have not thought about, that are not directly spatially related. And finding these relations becomes obviously more and more complicated the more objects, the more artifacts we're looking at. If you think of a repository that's holding millions of images, it easily amounts to a game of concentration, a memory game with millions of cards. You look at one image, you find something interesting, and then you search for it. You look at the next image, the next image, the next image. You do that over 1,000 images or so, and then eventually you have forgotten the object that you started with. So think of doing something like that, and not doing that with a single card and finding its corresponding card, but doing that for a lot of objects at the same time, and you can imagine the mental overload that you will eventually run into. Playing memory here with millions of cards is really challenging. So we're talking about image retrieval, but what a lot of systems so far have done when they rely on textual annotation is actually kind of a detour. Rather than searching for an object of interest, we're actually going into the metadata coming with each object and trying to find images where the metadata corresponds to the object of interest. Now, in that case, the relationship here between metadata and object and the image is somewhat unclear, right? Location is missing. And then there are all these other issues that I mentioned beforehand. Wouldn't it be more interesting to directly search with a query in a large repository of images, directly find the objects of interest, and what's more, not just find a discrete object, put these instances in relationship to another? so that we can then really go directly to the image content, rather search for text and then go back to the images. Now, easy said and done. Isn't there something like Google? Yeah, there's not just Google text search, but as you all know, there's also Google image search. And sure enough, let's take an image here, a nice photography of Golden Gate Bridge, upload that to Google image search, and that's what you find. A lot of other images of Golden Gate Bridge, and it seems like all perfectly fine. So image search seems to be solved. Now, I've been taking another picture here and uploaded that to Google image search. Helicopter in front of like snow. That was actually a large image, really large photography. And that's the results that I get there. No helicopter there, a bit of snow, or at least it's white in the background, and there's some red foreground object, mostly there. So why did it work so nicely in the first place, and why didn't we succeed in the second case? Both are red objects. Why doesn't it work in the second case? For the answer, we need to get a little bit geographic background. If you know the Bay Area, then this picture, which I've shown you of the Golden Gate Bridge beforehand, was taken somewhere here north of San Francisco, in a place where you can easily get by car, where a lot of people, as you can see here, are taking these pictures. That's actually something from Google Street View. And so you can imagine that a lot of people have actually been taking a picture from exactly the same spot. So in that case, and plus in the Bay Area, you have for a lot of time, you have nice weather, so the conditions aren't that different. So you get a lot of photography which looks almost identically the same. So the solution why it worked in the first case and why it didn't work in the second case is that people are somewhat boring. So what we call unique moments tend to be, well, not so special if you relate these images. Here, hundreds of unique, of these so-called unique moments have just been averaged, and you see how the spatial configuration, here, graduate or newlyweds, how the spatial configuration is somewhat always the same. We're not changing these roles, we're always the same. And that makes image search easy. So if you search for something that a lot of people have searched for, if you search for something, a picture that a lot of people are typically taking in the same manner, then you can easily find that. However, if we deviate in our picture, if I, for instance, search for this artistic rendering here of the Golden Gate Bridge, I get results like that. There's no Golden Gate Bridge there. In terms of colors, it might match, but the Golden Gate Bridge is sort of gone. And it gets even more embarrassing if you search here for gorillas, you get these results here, and it looks all nice until you spot that woman here, and then it's getting really embarrassing. The question is, why does something like that happen? And for that, you need to really understand how the search engine works. I mean, first of all, there's a lot of green here in all of these images in the background. Face and so on, color, that one can talk about. But most importantly, Google image search is also based on a text search in the background. And then you find this website here where there's this woman, and here there's some text on gorillas. And the algorithm doesn't know if gorillas matches this here or gorillas matches this here. And it leads to some confusion. Now, this particular problem here created quite some fallout in the media, and that's why you won't find this particular issue anymore. Once you figure it out, you can fix it. But you can imagine that you cannot fix all the problems at the same time, and that's why even a large company like Google is limited. So if you're searching for something like this artistic rendering of the Golden Gate Bridge, you're limited, or you might even face such embarrassing problems like we have here. The underlying reason for all of these challenges is therefore that computing and detecting similarities is really hard. There are a lot of situations where it's not so difficult. If I take text here, 2 words, pain and gain, I can easily measure a distance. Let's say they're here in terms of their Hamming distance, they're different by 1 letter. 1 letter is different. I can measure Euclidean distances in space. Just say how far are 2 points on this planet from another. I can measure similarity in terms of color. Lev Manovich, for instance, in this work here has taken large numbers of images, computed average colors, for instance, or color histograms, and related them with respect to another. That gives you an ordering like that. It looks fancy, but doesn't really get you to the content of the images. What we really would want is a similarity between two artifacts like that. But what makes these artifacts similar? What makes them dissimilar? How can we actually figure out this similarity? It's clear that such a similarity is hard to predefine. It probably has to learn, much like we actually learn it as little children, by being exposed to our visual world day in, day out. And that's something that we actually want to tackle. So the underlying question is the one that Kurdiovsky and other gestaltists posed some 80 years ago, this question like, why do things actually look the way that they do? What makes things similar? Why do certain things look similar and others not? And if I show you a simple example like this one here, we would all agree that, yeah, with this pattern here, these two here are similar as well. We easily get the ordering. But is that really the only ordering that you could come up with? How about this one here? Yeah? So what makes the shape similar and what not? Is this actually here 13, the number 13? Or is this a B? I mean, you see one, you say like, yeah, that context probably makes sense. Here it's a different context. And overall, like, how do you know about this ordering of numbers? That's something that we have learned and acquired. Our visual system, at the same time, has a lot of capacity, inherent capacity, that we also need to teach to a computer. If you look at this checkerboard pattern here, what would you say about A and B? Which one is darker? Which one is brighter? Yeah, I think there's kind of an obvious solution. Whenever somebody asks a question like that, people are a little bit reluctant. And yeah, for good reasons. If I show you this bridge here, you actually see, believe me or not, that A and B actually have exactly the same brightness. That's what we call color constancy. You kind of subtract the effect of a shadow to make your vision invariant with respect to shadows, so that objects in the shade don't necessarily look different to you. You implicitly correct for that artifact. Now we see that recognition is a complicated process, more complicated than we typically actually tend to believe it is. If I show you an example like that, you might even notice that yourself. Any idea what object we see here? I see a lot of shaking heads. Now, any idea what this is? It's much smaller, right? I mean, it's the same object. And here you can even see the individual brush strokes, the individual bits of paint. Now, I made it much smaller, and still you get it. So it's clear, like, in that case, context helped. But overall, recognition is more than observing individual dots of paint. It's more than observing individual pixels. There's a large semantic gap between the pixels that you see and the final concept of a boat on a sea. And as Max Wertheimer said, when I look at a rendering like that, what do I see? Individual dots of paint? No. I see boats, I see like the sun setting there, and so on. And that's actually where I eventually want to get. So besides these issues here, in a lot of situations, our visual system works amazingly well. And one of the reasons for that, I would argue, is that albeit being somewhat chaotic, our world, especially our visual world, is at large times highly structured. There's a large degree of order, a large degree of regularity, no matter what scale you go to. If you take a microscope, if you take your bare eyes or a telescope and look out in the universe, you will always find regularity and structure, symmetry. And these actually help you to learn from the past and walk into a room like this here, know that this is a chair, know about its function, and believe that it does the same thing that other chairs have done in the past beforehand. So there are a lot of patterns everywhere, and our way to tackle these patterns is to actually learn from the past for the future and then apply that knowledge. So the solution then actually has to be learning to see. Not directly hard-coding it, but teaching a machine to see by showing it a lot of images. Yeah? Having a computer just watch a lot of images ideally without requiring any additional annotations, just showing them the pictures because there are so many of them there. Annotation is costly, just downloading the images is not that costly. And then having an approach which actually bridges the gap between this large database of images and the computer. A computer vision algorithm, machine learning algorithm, which establishes relationships there, which reasons about them, which is then resolving all the individual conflicts, and then eventually constructs abstractions, comes up with concepts, for instance, so that we can actually learn invariances and generalize these concepts to new images. And this approach that I now like to follow is eventually guided by cognitive constructivism, somewhat based on Jean Piaget's theory of the same, and this inference process, which is eventually putting all of these images together in an iterative process, actually coming up with larger and larger concepts, is then the way to actually resolve these concepts and teach the machine without annotations to see. Now there are a lot of situations where you would probably argue that this approach has already succeeded, and that's true. If you take your mobile phone, you've probably seen that it can easily do face recognition. There's readily available OCR software processing text. But I would argue that there's a sharp distinction between these success stories that truly exist and a system that we might need for the humanities or art history, where you, for instance, find this particular artifact. Now, what's the difference? Why does it work so nicely in one situation or in a few situations? And in others, the ones that we are here really interested in, why doesn't it succeed there? And the reason for that is basically that there's a lot of training data for faces. People have cared about faces in the past. The same is true for text. But for this artifact, this particular artifact that you're interested in, maybe you're the first one who has ever cared about this. Nobody else has training data for that, and the other thing is there's no handcrafted model for that because probably nobody knows what this actually is. Yeah, and for faces, we kind of know how they look like. For text, we have an idea how it works. After all, people have been doing typesetting. But for this thing here, well, you're searching for it. And unless you know what it is, nobody else can actually tell you. So that's the problem here, right? So there we eventually want to go. Lots of images, no annotations. How can we actually learn similarity with only the single query sample that you actually do have? Now, I cannot go into the details of the algorithm. I just want to give you the essence from our previous publications there. And the essence is that you just take this repository, you pick one image, and you can easily find a lot of, or a few direct duplicates of that sample. Things which look almost the same like this sample. And at the same time, you're easily able to find a lot of samples which are definitely not identical. These things, the endpoints, you can easily find in terms of similarity here. But the vast majority of samples in between, there you're having a tremendously hard time telling what is more similar, what is less similar. So what we now do is start an iterative inference process which works, so to speak, from the ends and resolves conflicts. So we start with a single sample, then we find a few more samples which are similar, samples which are dissimilar, and given this individual sample here and the vast majority of images, we then train an approach to discriminate these few samples from the negative ones that we have here, and then have this constructive approach which explicitly reasons about conflicts. So if this here is our query sample and these here are similar, but these here happen not to be similar to another, then you better think what's going on, right? I mean, if this here has these guys as their friends, but they're not friends with another, then they should reason about how that actually should go about. If A is similar to B and B is similar to C, then A and C should also be somewhat similar. So transitivity, transitive relationships are then by time actually resolved, and that then gives you an ordering of large repositories of data. That is a tremendously powerful approach requiring no annotation at all. And if you apply that, you can, for instance, in a data set here of human poses, just without any training data, just show it samples and then have it reason about what's similar. And you get this poster here, and it directly gives you these years nearest neighbors, or here this tennis player serving, and you get other people, not just like female tennis players, but male tennis players and so on, serving as well. And you can do the same thing for objects as well. Yeah, so again, no information of object categories. You just throw in lots and lots of images from all sorts of categories and then have it figure out what's similar and not. And you kind of get these results here. Not all perfect, but without supervision, you get pretty far. So our goal is actually that we want to easily access visual content. And I would argue that a lot of the digital humanities so far have been on a very low semantic level, a low level of image understanding. There has been a lot of work in what we could call information technology, on image acquisition, manual annotation process, and so on. A lot on digitization, databases, image editing, and so on. But what we truly need is kind of a higher level understanding and assisting the humanities on a higher level of image understanding. Reasoning about individual objects and recognizing them, doing overall scene analysis, style analysis, bringing images there together. And where we really want to go? Well, Abi Warburg told us already 100 years ago. We want to turn these repositories that we had there from an arsenal of images actually to a laboratory which helps us reason about relationships, establish relationships between all of these images, find similarities there, and eventually easily open up the content in there and have this image data speak for itself, tell us its relationships, the story behind the data. That's where we want to go. And I strongly believe that these days we are actually at a turning point. The computational power has immensely increased and is now at a level where one could argue that we have almost human computation power easily available in a normal computer. We have large sets of images easily accessible, which you can just download from the from the internet. And then finally, the algorithms start to be there. I showed you an example before, and just in a few words, like how we were actually dealing with image understanding. So I think we are in a turning point to actually turn images from this like second or third class domain into what I'd like to call first class citizen of information processing. Make images central, yeah? With text, we've been able to do a lot of things which we cannot do with images, and I think that's time to change, and we can actually do so. So what do I mean with that? Well, if you look at text-centered processing, you see that with text, we readily assume that we have a lot of possibilities. We do word processing for editing text quite naturally. We analyze large sets of textual or number data in spreadsheets, for instance, and evaluate that. We can search for text in Google image and in Google with Google search and other search engines, and we can organize large repositories of text, for instance, in Wikipedia and other collections. Now, this here is definitely more than your ancient old typewriter, which was kind of the first way to, in a mechanic way, deal with text. Can't we have the same thing for images as well and turn them from kind of the age of a typewriter into something newer? Where are we? Well, if you look at image processing, I would argue that processing individual images is somewhat on the level of individual pixels. If you want to segment out here an individual part of this object, you cannot just say, give me the nose of that rodent here. You actually have to tell which pixels you want. If you want to analyze images, we can do this on the level, again, of individual pixels and their color, come up with a color histogram, for instance. But that's not really numeric analysis of the content of these images. It's just, again, an analysis of individual pixels. And if we search, well, if you search for this reliquary here, That's what you get. So it's not the same thing. So again, it's again this issue, right? You upload this image and eventually it recognizes that thing as being a table, and then, of course, everything else goes wrong. And just by the way, recent approaches in the humanities, here's a recent paper, have been actually utilizing an approach like that, where they've been doing recognition, first of all, using standard search engines, for instance, that from Flickr, to get you the objects. And then once you have the object, you can reason about the images. But if this object categorization goes wrong, you're kind of lost. That's why I would argue, let's directly do it in the image domain. Reason about similarities and avoid this detour over like textual annotations. And just by the way, this image here of this artifact, I was actually taking from Google image search. So it's definitely there in Google Images. I was just cropping this out and searching for the same thing here again. And Google wasn't able to find what it delivered to me a second beforehand. So Google image search is limited, and organization, well, taxonomies also have their limitations, as we were arguing beforehand. So if that's why I was talking about earlier on, we have, with text, left the age of the typewriter already. And we see the benefits of that. We see the benefits of hypertext and all these other availabilities that we have here. Wouldn't it be great if we would have the same transition for images, where we cannot access images on the level of individual pixels, but rather closer to the content, or a much deeper analysis? And then I would argue that digital humanities would get a new enabling technology that would actually enable future interdisciplinary research and open up new avenues of research there. Just to give you an idea that things are changing a bit, here's an example from some recent other work where you see different pieces of art, and 2 out of these 4 were actually generated by a computer. 2 others are man-made. Any idea which is which? I mean, if you know the pieces of art, that's easier. Any idea which is which? Okay, let's step to the solution then. This here is Mickey Mantle painted. So that's a human painter that has been painting him. This here is also painted by a human painter, by John Singer. The other 2 here are computer-generated pieces of art. So you get a sense that the computer has understood a little bit of style, superimposed that on some other images. We are leaving the age of individual pixels. What I now like to show you is avenues for turning the computer vision in the humanities into something a bit more practical than what we've seen in the previous slide, for answering standard questions that the humanities might actually have and pose to images. Questions of visual retrieval, reception analysis, doing a morphological analysis of individual images and relating them, authorship, style classification, and so on. I'll now walk you through a few of these examples. And let's start with visual retrieval here, first of all. So given just an image, let's say you're again searching for this artifact here. It's cropped out. Can I find other images where this object actually occurred? And without any further training, just marking this individual patch with a recent search tool that we've put together. That's the results that you get. They're not all perfect. You can actually correct it afterwards, then do another search. But that's what you actually get, getting closer to the actual objects. Let me show you here a video of that system actually in action. So you can pick an image, and then you can mark an area which you're interested in. This is just running all in a web interface. So you can say, this part here I'm interested in. And then you can also mark a second part. So you can really talk about compositions here. So let's say I'm also interested in that area here. And then I say they should have a certain spatial relationship with respect to another. I can say how rigid it is, or how loose that relationship should be. And then I can say, search me images where this composition occurs. That's here the results that this search tool then retrieves. You can zoom in into them, and then you can click through other results, find similar images. And you can see that they significantly differ in the style that they've actually here imposed. Some are colorized, others not, just drawings. These are renderings from the Sachsenspiegel, and not all Sachsenspiegel copies have been completed, so some look just like that, and still the search tool can actually nicely retrieve that. So that would be the mere search. Why is that important? Well, it's important to actually go beyond just a single style there and really establish longer range relationships, because not only creating something new in art plays an important role, but also the reception of previous creations and how they've been then altered over the time. So you want to understand what inspired an artist, how he has actually deviated from what has been done beforehand, what the relations are, and find these subtle differences between these different generations. And so what we worked on is identifying here in a large collection similar objects despite different ways of them actually being brought to paper or whatever source you actually have, or here as well, drawings, paintings, and so on. And we also wanted to allow for somewhat loose relationships between these objects, as you can see here. So if you search for these different persons here, identification can even find them in a somewhat loose spatial relationship with respect to another. This we defined or designed into this search tool specifically also for architectural search. So where you say, I'm interested in this structure here, and for me to search that structure, I want the system to actually find me, for instance, these capitals here, and then find the rest on top of it and mark that, and then you get kind of all of these detections here as well. So you can mark a lot of parts of an object and define their spatial relationship with respect to another. We did gesture recognition as an example, not just to find the gestures, but also to find these subtle differences which define the deviations between one gesture and another gesture, and then establishing automatically relationships between an object and other objects. For instance, between an oath that's been taken and the object, this reliquary here, that this wowing was taking place on top. So you want to figure out about the spatial relationship, how distant the person typically is, what angle they have to that object, and so on. So getting more into the individual image. But we also did exactly, on top of a lot of images, but also did the opposite. If you see a lot of objects, then argue not just about relationships within the individual images, but relationships between the different images, and for instance, figure out in a large collection of images who was actually drawing which one. So if you look at the Palatine Library, different workshops were actually taking place in putting that together, and the question was, can you actually classify, can you distinguish who was actually doing which? And there are different artistic workshops here, and the system that we put together then nicely sort of situated these different workshops relative to another, and you can run a classification task, get some accuracy, distinguishing them from another. Or you can take all of these different crowns here and ask a very simple question. If I take two crowns, what would be the missing link in between? Yeah, what makes them similar? What other things come in between? Kind of interpolate in between. And then you get like a 1D succession like this one. Just another example that we went for. You can do a lot of classical classification tasks, for instance, artist prediction, distinguish Van Gogh from Picasso, for instance, and do that for some few hundred, 600 artists here, and classify them. You get numbers, probably not so interesting here. Or do the same for different classes of style, predict them, how accurate they are, and then you get like in the top 3, how often you actually got the right category there. But what I found more interesting is actually predicting, for an instance, for the artist Picasso, other pieces of art by other artists that kind of are similar in style, something which you don't directly get from the annotations, but you ask then, like what other pieces of art are somewhat similar to Picasso, and that's what the algorithm then eventually retrieves. And just to give you an idea, these here are actually artworks from Picasso. And I think you get a sense that there is actually some similarity, and also Picasso had quite a spread in his oeuvre, which the algorithm has then also nicely captured. While this is like more a coarser analysis as opposed to for an individual artist, we also try to zoom, so to speak, zoom into individual pieces of art and look at an image and a reproduction and figure out the very fine-grained, subtle differences between the image and the reproduction. And these here you can see by means of these tiny little quivers. And it turns out that if you do such analysis and you look at this young fellow here, then his torso is actually slimmer in this reproduction than the original, and the rest of the body is somewhat retained, so they made him kind of a little bit slimmer. Subtle differences which are probably really hard to see, especially if you look at a large repository of these pairs of images. But in the algorithmic fashion, you can nicely sort of find these subtle differences here very easily, highlight then differences between pairs of images so that you can easier spot them, or here in Michelangelo's reprints, find also like how the body posture like in a tiny manner changed, so that then this would become an enabling basis for future research, another asset. Now, I've been talking a lot about images, and in a very final note, I actually want to show something also for script. So we did all that image analysis and put together that tool here, and then I was asked by Assyriologists, this was a cooperation, or this is an ongoing cooperation with Stefan Mauer in Heidelberg, if we couldn't do something like that also for much more complicated script for which existing OCR just does not work. For instance, for ancient old cuneified writing. We took that system and trained that, and you can then here see a lot of examples of the individual detections. The system kind of gets an idea of the lines in the text and then comes up with a probability of each individual script being there, detects it, gives you a transcription of that to numbers in that case. And I can give you a brief overview of the same system that we've seen beforehand here run on cuneified script. Let's just scroll that forward. Let's pick a clay tablet here and then do the detection. Okay, algorithm runs there, all that clay tablet, and then outputs the detection of individual script that it found, gives you the transliteration for that. And afterwards, so here are the results. You can actually toggle here the level of confidence if you just want the very confident results, or if you want to get all the results that are potentially conceivable. I can slide it back and forth and you get more or less results. And then you can zoom in the individual results. And for each of them here, for instance, change the transliteration that you want, correct that, then retrain the system with that, the same way that we could do it with the objects that we've seen beforehand. Here you can go through your dictionary of objects, or in that case, script that has already been detected beforehand. And, well, if you do that, that's kind of the results that you get. Green here would be all picture perfect results. Red are things that the algorithm in the second round then would try to get right. And by that, actually learn the script. Now, to kind of summarize, I want to conclude with a few remarks and also questions to you, the audience. We've seen examples of individual image, but also, in particular, examples of large-scale data analysis in the humanities. And I would argue that there is something unique about the humanities, which probably differs it from other large repositories, for instance, the ones that you find on Facebook. And a lot of these here, you have these phenomenon, this boring phenomenon that we showed beforehand, and people probably don't care so much when they do an analysis of that about the individual, I don't know, graduate that you, for instance, have there. You just care about the average statistics that you have. In art history, You probably care about the Mona Lisa, and not just like all paintings being averaged. You care about the individual, but you at the same time, you do also care about the relationships of this individual to other pieces in this oeuvre of the same artist or even that of different artists. Yeah? There might just be one Mona Lisa or just a few Blue Mauritius, but these relationships matter as well as the individual one. So my question would be, which questions do you actually want to pose to this large repository of images? Which questions do you want to pose to the individual image and want it to be answered? A second question is this question of where are we relative to what I would call a semantic barrier. So you might argue that there is still this dividing line. It's probably going to be there for quite a while, that it's hard for a computer to cross. On the other end, you might have human-level intelligence, whatever that is, maybe like the level of capacity that a scholar has in a certain discipline where they're trained, art history, for instance. And the computer does not have that ability. Do we really want to replicate that ability? Do we really need to replicate that ability for our computer-based analysis to be helpful? I would argue that aiming for this artificial research system that's fully automatic is probably not what we actually want. What we want, and what's much more likely that we can actually get, is a computer-supported analysis which is not fully automatic, and for good reasons not fully automatic, because we want to have a closed loop of the algorithm and the expert coming up with proposals, and the expert verifying them, resorting them, and then giving them back to the algorithm. And in that sense, creating a new level of knowledge. I would argue that the expert and the computer are somewhat orthogonal. And I've seen a lot of discussions about the computer trying to just replicate what the historian, for instance, can do, what the scholar can do. But I would more urge you to think of ways where a computer can give us something which is orthogonal, and in that sense actually create a new kind of research rather than just doing the same research a little bit faster. So my question here is, where's your need for complementary competence? Where's your need for something that's not just replicating what you're doing? I mean, that's also great, as we've seen beforehand, speeding that up. But where's your true need for something which is potentially complementary to what human level of analysis can do? So let me conclude. I see a critical need for the digital humanities beyond of classical information technology, as we've seen. I see a large potential for an analysis that establishes these long-range interactions beyond a single artifact and puts things into context which you probably would not have conceived beforehand. For the medium term, for the intermediate future, I see a lot of potential in computer-supported as opposed to a fully automatic analysis, and I see a lot of value in a closed loop between the algorithm and the expert. I think that the true problem of understanding images and the content therein is a really large undertaking, one that's too large for just a single discipline, one which calls for interdisciplinary research and bringing the different fields together and utilizing all the capabilities that we have in the different image sciences, for instance. And I think that these underlying epistemic questions that we have there are really interesting and should be answered by all of these disciplines. And to conclude, I think that visual analysis is now starting to become an enabling technology which eventually improves the accessibility of visual data and thereby gives rise to a new kind of research that actually becomes that we actually become able to see. And I'm really curious to see this happen. And I hope you also. So I'm open for questions. Thanks.